I'm Samar Kansal, and alongside with Tanya Dinesh, we are presenting our study on optimizing computational resources in large-scale system through advanced load balancing algorithms. So aim and approach. Our project uniquely employs a simulation-based approach, leveraging real-world data from NREL Eagle supercomputer. We have constructed a simulated environment using diverse server models to accurately measure the performance of various load balancing algorithms. What are the data aggregation and research questions? A significant part of our work involved adapting large data volumes for our C++ simulation framework. This allows us to include real-time usage patterns and job characteristics. Our key research questions revolve around how different algorithms affect server efficiency, understanding resource demand patterns, and tailoring algorithms for optimal performance. So let's dive into some key load balancing algorithms that we have studied. Round robin scheduling, weighted least connections, least response time, and least bandwidth. Use cases and selected criteria. Each of these algorithms cater to specific use cases like ensuring efficient and reliable traffic distribution across servers. The choice of algorithm is not arbitrary. It heavily depends upon the specific requirements, the type of the job we have, and the characteristics of the system. So, impact on what is the impact on modern systems? In today digital landscape, these algorithms play a vital role. They are not just about managing server loads. They are essentially maintaining the stability and efficiency of modern applications and website, ensuring optimal workload distribution. Now, I'm gonna walk you through the design and file structure of our project. So, our project is basically divided into four parts. We have data, we have our client node, and we have our model, that is the actual simulation that we are executing using C++, and then we have the server file, which is basically a bridge between the client and the server. So in and all, we have created a web application that I will be demonstrating in upcoming slides. So that web application, that web page is communicating through the C++, the execution of C++ our models through the server. So we are making a API request to our server, and the server is kind of executing those commands and algorithms and simulating all the with the data that we have on the client side, and then we are outputting the result on the client side. So on the data side, let me show you how the data will look like. So this is the data that we pulled from the open source supercomputer uh, data repository. So it has a this is a JSON file, and each object in the JSON file represents a kind of job that we have. So it gives us a lot of information about the job, like what is the node list, or what are the type of the node that they used, and what was the submit time, and what was the start time, what was the end time, how much power it took. So it has a lot of parameters that we can take account into our simulation. And this is the data that we will be using to simulate the various algorithms. And this is this is the actual simulation directory. So we have defined various algorithms in our load balancing file. So this is a file that contains all the load balancing algorithms, and this is kind of interface for all the algorithms. And this is a model class, and similarly we have a node class of to handle the number of, we will be inputting the number of nodes, so it will be creating uh, those many nodes object based on the input number. So we have node, and we have other utility functions here. So now coming to the demo part. So coming to the demo part, let me quickly start my server. This is the client. sorry, let me start the server first. Server started. So I have to restart my client. So now client is running at 3002. Let me pull on 3002 here. So this is the web app that we have created to get the user input for the simulation. So we can enter number of nodes. So let's say I will simulate the number of nodes as 10, and this is the queue size. So for our simulation we are providing like we are simulating for both like multi queue system as well as a single queue system. So we will be outputting the data simulation results for both of the queue types. So here we can define the queue size. So let's say our queue size is 5. So number of jobs, so actually number of jobs is kind of like see if, like for this data file we have a lot of jobs. Like this contains millions, I guess, I don't know, lakhs of millions of jobs. So we can select the top 10,000 of top 1 lakh jobs. Let's say I will select 1 lakh jobs from this data file. Now we have to upload the data file. So it will take the JSON as expected, and here we can select the simulation algorithm that we want. So we have round robin, random, utilization based, least connections, and we can also select all algorithms. So first I will go with the round robin. So it started executing. So I am outputting the results on the server side also. So as you can see, this is the metrics that we got, as well as I am giving an option to download the PDF file. So I'll just save this PDF file quickly. So coming to the output file, so this is the output that we are getting from the simulation. So we ran the simulation for 10 nodes, and we selected round robin, and 5 is the queue length job, and we gave 1 lakh jobs as the number of jobs, and this is the result that we got. So it will output for the multi queue system as well as for the single queue system. So for multiple queue system we are getting the results for every node. So since we outputted 10 nodes, we will get id, this is the result for the first node. So since we use the round robin is will divide the number of jobs equally. That's why we are getting like for each node we are getting 10,000 jobs. So that was expected, and these are the parameters that we are getting. So and similarly for the single queue, we have some rejection amount. Like it depends upon the queue size, and if our queue size is small enough, then we will get a high rejection amount. So we are getting some rejection amount, like 1.6% of the jobs are rejected. And in a similar fashion, we are outputting the metrics for each of the node. So we can select instead of selecting a single algorithm, we can select it for let's say this time I will give queue size of about 10, and number of nodes, let's say I will give 15, and number of jobs, let's say this time some random like number, and I have to input the JSON again. And instead of selecting the round robin, I will select the all algorithms so that it will simulate all algorithms. All algorithms, I guess it will take some time, so we can monitor the output in our server. Take name and the excuse me. Yeah, we are heavily depending upon the submit time and the start time and the actual end time of the process. So for as of now, like we are taking these parameters into our study, and based on that we are simulating the our load balancing algorithms. So I will just so the simulation is ready, so we can check the result. So as expected, it ran all the algorithms that we have. So for 15 nodes we inputted 15 nodes, and this is the first is the round robin. then we will get for random algorithm, and similarly we will get for utilization based algorithm, and similarly we will get for least algorithm. And so this is the client that we have implemented, and this is the result. So coming back to the slides. So I just wanted to explore like what are the why this study is useful, why our tool can be useful. So let's explore like how selecting the appropriate load balancing algorithm is crucial and heavily depends on the type of the job a system handles. So let's say we have a small CPU cycle intensive jobs. So consider tasks like quick computation or data validations. These are the typical based in a single CPU cycle. Here, algorithms like round robin or least connection are ideal as they distribute these numerous small tasks evenly, preventing overload on any single server. What about addressing large resource intensive jobs? On the other hand, like for larger jobs like complex data processing, which require significant resources, algorithms like weighted least connections or least response time are more suitable. They ensure like that server with greater capacity or faster response time are utilized, thus maintaining efficiency without causing delays. So in a scenario with mixed type of job sizes such as web services that handles both simple queries and data intensive requests, algorithms like least bandwidth or weighted round robin can dynamically adapt. So we can actually like test every algorithm like through our tool. Like we can assess, okay, this is the jobs history that we are getting, and based on the job history, then we can based on the metrics that we are getting, based on the like okay, so for this round robin algorithm we have some rejection amount, but for the other algorithms we don't have rejection amount for this type of data. So based on that job type, based on the job sizes, we can select a balanced workload distribution. Like we can select an algorithm that will be that will ensure a balanced workload distribution. What are the future direction and enhancements? Because of the uh, because of the limit of our time, we could not implement fully functionalities into our project. So as we think about the next steps to for our project, we aim to delve deeper into the strict dynamics of server utilization. Future enhancements will involve incorporating more detailed parameters such as the actual usage of nodes and the power consumption associated with different job types. By adding these layers to our simulation, we can achieve a more holistic understanding of server performance and efficiency. Moreover, the integration of machine learning stands as a promising frontier. Imagine developing ML algorithms that can analyze extensive data sets, considering factors like node usage, power consumption, job size, and runtime variability. These algorithms could then predict the most effective load balancing strategy for any given scenario. Ultimately, our goal is to move beyond static algorithm selection towards a dynamic system where load balancing decisions are made more intelligently, adapting in real time to the ever-changing landscape of computation workloads. This evolution could significantly optimize not just the performance but also the energy efficiency of large-scale computing systems. In summary, our study underscores the importance of selecting the appropriate load balancing algorithms based on the specific system needs, using simulation with real-time data. As we look forward, the evolving landscape of computational demands will undoubtedly shape future advancements in load balancing technologies, paving the way for more intelligent and efficient system. Thank you for your attentions and have a good one.